Hi, we have another example force problem, and this is kind of a little more difficult, well, it is more difficult than the previous one, and this one also involves an incline. So, what do we have today? You are trying to push a 50-kilogram couch, it's pretty heavy, up a ramp into a moving truck. The ramp is at an 18-degree incline. If you push with a force of 350 newtons upslope, the couch moves up the ramp at a constant velocity. What is the coefficient of friction between the couch and the ramp? All right, that's our problem. Our problem-solving steps, draw a picture. So we're trying to push a couch up into a big truck. So couch, person, Okay, there's our picture. Knowns and unknowns. All right, the mass of the couch is 50 kilograms, and the angle is 18. You push with a force of 350 newtons upslope, okay, and it moves up at a constant velocity. I like those words because that means there's no acceleration, balanced forces, easier math. What is the coefficient of friction? Okay, so what is the coefficient of friction? Well, what's the object of interest? It's usually the thing we have the mass of. It's the couch. So the object of interest is the couch, and we're going to draw the force diagram for the couch. So what forces act on the couch? Earth is pulling down. I always like to start with that. Earth is pulling down, that's our weight. The ramp itself is supporting the couch. It's holding it up, and that's the normal force. And remember, that's always perpendicular to the surface. We're looking for something about friction, so there's clearly friction. We're trying to push the couch upslope. Friction is going to be trying to keep it away from that, trying to avoid that. So friction is going to be downslope, and we are pushing on it. So the force of our push and anything else. I think that's it. I can't think of anything else that's physically interacting with the couch. It's the ramp, us, and the earth. Okay, we have our force diagram. Are we balanced or unbalanced? Okay, oops, coordinate system, I forgot. Well, I forgot. What direction is the motion? So the motion is in this direction, which means I'm going to choose a coordinate system on the incline. Plus x and plus y. And again, if you choose something and kind of say x and y are this way, that's fine, doesn't matter. We'll still get the same answer. All right, balanced or unbalanced? So in what I've chosen as the x direction, is there any acceleration? Well, no, because it's constant velocity. So we have a constant speed, which means there's no acceleration, and if there's no acceleration, forces are balanced. And so the forces have to add up to 0. And in the y direction, that's this one, is it even moving? No. There's no motion. So, no motion, which means no acceleration. Oof, squeaky markers, sorry about that. Balanced. We also have the forces have to add up to 0 in this direction. Okay, now we're going to do our force table. I have 4 forces, and I'm going to break them up into their x and their y components. Okay, so 4 forces. What do I have? I have the normal force, I have friction, I have the pushing force, and I have mg. I'm going to break those up into their x components and their y components. All right, so this is what we have. Normal force. All right, that's the normal force. What direction does that align with? Well, the normal force, so again, if I put my pen like this, that's positive y direction. There is no left-right component to this. It's all in the positive y direction. So normal is all in the positive y. Friction force, that's this way. That aligns with the x direction. There's no up or down, and it's in the negative x direction. The pushing force, that's this. Pushing force is positive x direction. So we have positive pushing force there, and again, nothing left or right. Weight, and then that's this. That's in both directions. So we have to break the weight force up into components along the x and y directions that I've chosen. And again, if you draw your triangle like this is just something I suggest you write down or you help with. Memorize it, whatever. This angle, this top angle is the same as the angle of the incline. So if you draw your triangle like this top angle is that same incline angle. Which one is x and which one's y? Okay, x is this one, that's the same direction, and y is this one. The x component of the weight, that's this piece, and it's opposite my angle, so katoa, that's the sine component. So this is mg sine theta. Is that positive or negative? In this case, it's negative, because it's going kind of to the left. You know, my angle is down and left. Then the y component, this one, adjacent, so that's this cosine component, mg cosine theta, and that's down, that's negative as well. All right, so we have our forces all broken up into the x's and the y's, and we know that in the x direction, forces have to add up to 0. We know in the y direction, forces have to add up to 0 as well. So let's do Newton's second law. Okay, Newton's second law. X direction and y direction. You can see I'm doing a little bit of a shortcut here. We know that it's normally sum of the forces equals ma, but I just said we know the forces have to add up to 0. So I can just say sum of the forces in both directions is 0. Let's add up the forces in the x direction. Add the forces in the x direction. Negative friction plus the pushing force minus mg sine theta, and then that equals 0. Y direction, plus normal, nothing, minus mg cosine theta equals 0 again. Okay, again, this and this, these two equations are the key for solving force problems. Do we need the friction equation, the fun equation? Absolutely. Because that's what we're trying to solve for. What is the coefficient of friction? So how do we solve for it? Well, we want to plan our solution. And this you can do in multiple ways, but what I do is I just start with the thing that I'm looking for. So what variable am I looking for? That is the coefficient of friction. What equations have the coefficient of friction? There's only one. But we need this one. So F equals mu n. That's got mu. In order to get this, I need F, and I need the normal force. I need the friction force, and I need the normal force. How do I get the friction force? Well, hopefully I can get it from here, because that's the only thing I've got. That's what I'm looking for. I know how big the push is. I know the mass, right? Yep, I know mass, I know gravity, I know the angle. Got it. So I'll get this to give me friction. Normal force. Okay, mass, yep, gravity, yep, got it. Okay, so I can get the normal force from here, I can get the friction force from here, pop those both into this, and we will have our coefficient of friction. All right, let's do it then. This one, I need to rearrange it so I get friction equals something. This one I need to rearrange so it's normal equals something. That one's the easy one. Just pop that over to the other side, it becomes positive, there we go. Friction. Bring this over to the other side. Oh, it's not bad. Okay, bring that over to the other side, it becomes positive, and I'm left with push minus mg sine theta. All right, now I'm going to put that in for friction. I'm going to put this in for normal. So left side of the equation, F push minus mg sine theta equals mu times mg cosine theta. Got it? We know that. This will work. Now you might stop and say, can I get rid of anything? Are there any zeros? Is there anything that would cancel out? And you see an mg in both of these, but you cannot cancel it out. Don't do it, because this term doesn't have mg. In order to cancel something out, it has to be in every single term. So, can't cancel anything out. So what do we have? Okay, this time I'm going to just put the numbers in at this step, just because that's helpful for some people. So the pushing force was 350 minus the mass, which was 50 kilograms, times gravity, just the number, remember. Sine of the angle was 18, equals mu times mass, 50, gravity, 9.8, cosine of 18. All right, grab your calculator and see what you get if you make these calculations. What do I get? I get 198.6 equals mu times 466. Oh yeah, that'll work out well. Mu equals 0.43. That's what I got. Again, don't stop there, don't stop there. Check for reasonableness, check for units. Well, units, there's nothing, so we're fine on units, because it's just the coefficient. And is it reasonable? Well, mu is typically between 0 and 1, sure. 0.1 is really icy, 0.8 is really sticky. This is right in the middle, and it's a couch going up a ramp. I would say that would be, sure, that seems reasonable. If it was, 0.1, I'd say no way. If it was 0.95, I'd say, So I think it's reasonable. We have the right non-unit. And we've answered the question, I think, because the question was, what is the coefficient of friction? Yep, okay, we've done it. Ta-da! Look, there's another problem. So this was just, again, the process of going through, and I was just talking through the steps and not making them explicit this time. And you'll see in later videos that I'm doing it with even less explicit this, then this, then this. And as you get more comfortable doing force problems, you'll start to be able to jump and just say, oh yeah, that's what's next. Oh yeah, that's what's next. Hope this was helpful. Good for you for watching.